Yeah, as I mentioned, our first speaker for today is Riley. Riley joins us from Vancouver, Canada. I mentioned that, we're seeing like a more diverse distributed geographical presence, which is great. He's currently a senior software engineer in the machine learning platform at Autodesk. He's worked at few other companies before, also kind of sort of in the MLOps space. He was a senior machine learning engineer at CoreZero, a data scientist and an MLOps engineer at Cisco. And then currently he's part of the Autodesk Machine Learning Platform team. They use Metaflow as the primary foundation for their managed training infrastructure. So yeah, we'd love to learn more about, Metaflow's use cases in the Autodesk Machine Learning Platform and anything else that you would like to share. Thank you so much, Riley, for joining us, and over to you.
Oh, cool. Thanks, Sri. Okay. Cool. So yeah, as Sri mentioned, I'm part of like a founding core engineers building an ML platform at Autodesk from scratch. It's kind of a unified platform. AMP stands for Autodesk Machine Learning Platform. Um, so we evaluated a lot of different orchestration tools, but landed on Metaflow as we like that it could be used for a variety of different applications, like data, compute, orchestration, and versioning. So you got a lot of value in a sense. And we were looking for an orchestration tool that would allow our users to construct machine learning pipelines, chaining together different tasks in the end-to-end ML workflow, all the way from data preparation to model training and evaluation. At Autodesk, we're kind of boxed into using AWS as well. And that's another reason that we chose Metaflow, in that it kind of makes use of a lot of different AWS managed services. And given that it provides a nice wrapper for running AWS batch for scaling out our workflows, so that users can leverage this function to simplify the process of building and training models. We were also really elated to discover that reproducible experiments are the bread and butter of Metaflow, especially since we can version pretty much everything, including flow runs, data snapshots, artifacts, and it keeps track of all the flows and experiments. So this was important in terms of data lineage for us. And then a nice benefit as well is that Metaflow could be leveraged as an experiment tracker. And we're sort of using it for that use case. So again, there's tremendous value there. But I think the biggest factor was human-centric UX. One of our biggest worries would be building tooling that wouldn't be adopted or used by our users, especially since some of them are using, there's a bit of tech debt in our organization. So some users already have their own bespoke ML platform. So there was going, for them to adopt our approach, it would need to have a really strong UX. So that they feel more motivated to transition to our platform than their own bespoke ML platform. So this is a high-level overview of how we've integrated Metaflow into our managed IDE, and we're using SageMaker Studio for our IDE. We call it Ham Studio, and it acts as the productivity suite for developing and training models. In order to access Studio, users interact with the UI, which in turn spins up their own personal Studio instances. Once they are logged into the Studio notebook, they will have access to various tools. Metaflow is one of those tools users can leverage to create and orchestrate ML pipelines, run reproducible experiments, perform training at scale, and then they'll be able to monitor their workflows through the UI. Additionally, users will be able to bring in their own data, which both Studio and Metaflow will have access to import. So this is just a very quick, like we're really early in our, we're really early in our training infrastructure. We recently just rolled out to 50 users, so we quickly had to put together just a pretty basic UI for now, but it does the job. Basically, it authenticates and authorizes the data scientists and allows them to spin up their own personal Studio instances. So each team is assigned to a different project domain, depending on their team. And then the login is controlled via SSO, and then they'll be directed to the Studio launcher page upon authenticating. And then we made available a custom security hardened image that has everything the user needs to run Metaflow jobs from their Studio notebooks. So when they create a notebook, they're prompted with a menu where they then select the Metaflow kernel image and a startup script. And then this kernel has Metaflow and Mamba baked in, and then it sets Metaflow home so that it points to the Metaflow configuration file. And then all the user needs to do is do %% bash and then run their Metaflow flow from within the notebook cell.
Quick question here, Riley. Is that okay, or should we wait for at the end?
Sure.
So a couple of questions actually. Then, so one is just the UI that you mentioned about like a bare bones UI just to authenticate a user.
Mm-hmm.
Is that something that you guys had to build, or is it possible to build that in SageMaker Studio?
We built it separately from SageMaker Studio. So what it does is it's like connected to an endpoint, and the endpoint creates a pre-signed URL, and then the pre-signed URL launches the Studio instance.
I see. Okay. And then secondly, like, so SageMaker Studio would be running in an AWS account. So when the user eventually gets to, let's say, the notebooks, those notebooks would be running in the same AWS account in which SageMaker Studio was. So that's where the backend instances would run, or that's where, like, I'm guessing AWS batch instances get created later and stuff like that, right? So it's one account. They don't have to worry about like, figuring out how to, if it's a different account, you log in separately into that account, do the same thing on that side. Is that right?
Almost right. So
would
it be each team actually, so our organization handles multi-tenancy a little differently than conventional. It's kind of unorthodox, but every team has their own AWS account. So we provision Studio and Metaflow into each of the different stakeholder teams' accounts.
I see.
And then from there, it'll provision access to Studio from within their specific targeted production account. And then that account also will have Metaflow
I see.
backend. So it's like N accounts per team.
Got it. Okay. Sounds good.
Cool. So so this is the Studio interface that has a launcher button that basically launches the Metaflow UI directly. So Studio is quite customizable. So we can create a simple lifecycle configuration in Studio, and that configures the Jupyter Server proxy and Nginx so that users can view the Metaflow UI from the Studio notebook. Also, when the user runs a flow, there's a link provided to the flow run in the UI so they can navigate to it directly. That's the UI. So this is our current Metaflow infrastructure using AWS managed services. So firstly, users execute all Metaflow runs from SageMaker Studio. So Studio serves as the point of entry, in a sense, for access to the Metaflow metadata service endpoint. We took care of security hardening every component, and a lot of the components are leveraging inner sourced security hardened Terraform modules. The Docker images used for the UI, metadata service, batch default image, and Studio kernel are based on in-house images provided by our security team. And then there's a patching pipeline running on a regular cadence that refreshes and patches these images as well to ensure no security vulnerabilities detected by Orca. And then for orchestration on a schedule, we are leveraging step functions. So any failed executions on step functions are sent to a Slack channel for alerting. And then finally, we lean on AWS Batch as the compute layer for scaling flows. And again, the AMIs used for these EC2 instances provisioned through Batch are all using security hardened AMIs. And this infrastructure was vetted by our security team. we had to go through a formal approval from security through an architecture security review. So that was like the bulk of the work, just making sure every component was that like security hardened. This is like a really simple thing, but actually we've got a lot of rave reviews from our users in that we compiled a lot of different examples of using Metaflow and like a Metaflow demos repo that our users can peruse to explore the capabilities of Metaflow. It's something really simple, but has received a lot of positive feedback. So we've curated like examples of fine-tuning an LLM using deep speed, fully sharded data parallel, distributed data parallel within Metaflow. We have other examples too, like auto tuning, experiment tracking with our managed TensorBoard instance, parameter efficient fine tuning using Hugging Face's PEF library. So chances are you'll find like a use case, our users will discover a use case that somewhat resembles what they want to do, and then they will have like a guiding template that they can follow to make it easier when they build their own custom flows. And
This
then we've
looks
also,
awesome.
oh, thank you.
Sorry, I just said the examples repository looks awesome because it is one of the more common things where people are like, oh, how do I get started with a specific use case in
Right.
mind? So if there is an existing example, either you can just run it or you can templatize it or use it as a template and then figure out. This is pretty cool.
Yeah, exactly. And then we've also created a cookie cutter template that users can use to easily create their own custom projects structured with Metaflow. It enables consistent and strict naming conventions of flows, projects, and tags. So the user basically initializes a repository with some project values, and then it produces a templated repository with templated flow code. And then these are the values that the user enters to initialize their Metaflow compatible project. It will keep their flow standardized. But the cookie cutter template does more than provide structure for a data science project. It also plays a huge role in how users run their flows in production using step functions. So this is still relatively immature, and we'll likely see further iterations in the future, but we at least have like a basic working GitOps pattern for production workflows. And here's how it works. So basically users do model evaluation, and then they choose the Metaflow run that produces the best configuration. And then they tag their designated run with ready for prod ready, the prod ready tag. And then the user commits their code from Studio, including the Metaflow flow, pushes to the repo, and then creates a PR in our enterprise GitHub. And then the push event is detected in the GitHub repository. The PR triggers testing for the branch in Jenkins. And then it runs unit tests for the individual modules with PyTest. Optionally runs the flow itself, and then Jenkins invokes a Lambda function via Spinnaker, and then the Lambda retrieves the Metaflow config from Secrets Manager, runs the flow on step functions. Once the PR testing / review is successful, then you merge to main, and then the merging to main triggers the Jenkins pipeline, performs the unit testing for flow validation. Again, Jenkins invokes Lambda via Spinnaker. Lambda pulls in the Metaflow config from Secrets Manager. And then the Lambda uses the Metaflow client API to ping the metadata endpoint and checks that the corresponding flow has the appropriate tag. And then AWS Lambda uses the Metaflow namespace, the global namespace. Lambda pulls in the code artifact from the flow run, and then also uses the Git hash to download the Git repo, and then it compares that the code is the same between the two. And then lastly, Lambda compiles the flow and then maps to the step function orchestrator. And then it adds the Git hash as a tag in the designated flow run after it's after it invokes the step function.
So sorry, one quick question. So in this case, when you say Metaflow flow is deployed in production, it is deployed as an AWS batch job?
It is deployed as a step function, or
Oh, it's
compiled
deployed
as
as a
a step
step.
function.
Okay. Okay.
So
Cool.
like Python flow.py -- production
Hmm.
step function
Yeah.
create.
Yeah. Yeah. Okay.
Um, and then this is the cookie cutter that initializes the project so that the user can interact with the CI/CD pipeline and push their flow into production. Note the unit tests, note the Jenkins file, and there's a run step function shell script. So basically, the user modularizes their code as internal libraries in the SRC folder, then imports them in the flow file directly, and then they write unit tests against those internal modules in the test folder. And then user can either push to a branch in which it triggers an experimental deployment on step functions, or create like a PR merge, and then it'll merge to the main branch, and then it'll trigger a production deployment. And then we have a Lambda in place to monitor failed step function execution. So if a production flow fails, it'll trigger a Slack channel alert. And that is our orchestrator process. Very simple. It'll be refined, I'm sure, as we get more feedback. Now on to distributed training. So we've been making heavy use of Metaflow's parallel decorator, which runs AWS batch multi-node parallel jobs to run distributed training. We found it quite straightforward to initiate a gang scheduled cluster. You simply need to specify the number of nodes and the num_parallel argument, and then wrap the subsequent step in a parallel decorator. So we have battle tested AWS batch multi-node distributed training using a variety of different distributed computing frameworks such as Hugging Face, Accelerate, PyTorch, Lightning, DeepSpeed, and also TensorFlow distributed. And we have curated examples of each of these in our Metaflow demos repo. And our users are currently playing around with some of those demos. And then we monitor the GPU, CPU utilization of our distributed training jobs using the Metaflow GUI. The custom GPU profiler decorator is helpful with this. And then the GUI shows the execution of the distributed training job for the worker nodes and the head node. We also provide out-of-the-box CloudWatch dashboards as well that show the GPU, CPU utilization if the user opts not to use the GPU profiler decorator. And then we are also in the midst of experimenting with TensorBoard profiler to also display these system metrics on our managed TensorBoard instance that we have plugged into Studio, similar to the Metaflow UI. And then from the monitoring GUI, users can click into each node for logging, and then they can view the progress bar by inspecting the control node logs. And then we created several batch queues, each with a different instance family, and users can select the batch queue in combination with their requested number of GPUs, CPUs, and other resources, upon which Metaflow will select the best instance type for the training job. And then we also support batch queues for spot instances as well. So one of our data science research teams is really heavily invested in using Ray to train their model. So this was at the time a little bit of a blocker because we needed to figure out a way to integrate Ray with our managed training infrastructure powered by Metaflow, especially since we already decided to go with Metaflow. So we had to find a way to ease their transition also into adopting Metaflow. So one thing I learned was that Ray was simply just a framework, and Ray doesn't necessarily compete with Metaflow. They are very much complementary of each other. So actually, the more apt comparison would be Ray's VM launcher versus AWS Batch. So what I was curious to see is if we could run a Ray cluster using AWS Batch multi-node parallel jobs. And since Ray is quite extensible, we discovered that it was in fact possible to use Metaflow to orchestrate the creation of the Ray cluster. So Batch handles the infrastructure, setting up the drivers and workers, while Ray optimizes hardware usage. So we use existing abstractions from the parallel decorator and then teamed up with Outer Bounds to introduce a Ray parallel decorator. And then this Ray parallel decorator can essentially decorate a step and then subsequently set up the necessary hardware using AWS batch multi-node. And then users just need to insert their Ray code in the step. And then during execution, Metaflow starts the transient Ray cluster, runs the Ray application, and then subsequently shuts down the cluster upon task completion. So we have battle tested the Ray parallel decorator and used it to fine tune a 6 billion parameter model, as well as a variety of other applications and use cases. Using DSpeed and Ray Train, the fine tuning job completed in about 50 minutes, just using 16 A10 GPU nodes. And the Ray logs are displayed in the Metaflow UI, so users can monitor their Ray application seamlessly. There are some caveats, though, with this integration. So it doesn't support heterogeneous clusters, mainly because AWS Batch Multinode doesn't support heterogeneous. So currently all node groups in a multi-node parallel job have to use the same instance type. It doesn't yet support specifications of several different instance types and availability zones in the Ray cluster autoscaling config, such that when spot instances become unavailable, smaller instances are created. And these are some of our benchmarking results when we collated collated from running a distributed fine-tuning job on Metaflow using AWS Batch Multinode. So we tested on 2 to 4 nodes, with each node having 4 A10 GPUs. So all the tests were using PyTorch Lightning in conjunction with DSpeed. Activation checkpointing was turned on to increase the throughput. And then we offload the optimizer to CPU to decrease GPU memory footprint. So the model was T5 3 billion parameter transformer model. The results show that 4 nodes with 16 GPUs in total was more efficient and cost effective. And then this is our Ray Train plus DeepSpeed benchmarking on a different model. We use the 6 billion parameter GPTJ model. So that's a separate testing event. And then we're continuing to enhance our distributed training infrastructure with AWS Batch, and that includes setting up high performance computing, which AWS has enabled for Batch. So there are 2 facets of HPC. So the first is Elastic Fabric Adapter, which is a networking feature that's attached to EC2 instances to improve internode communication. So when working with larger models and enormous amounts of data, internode communication becomes a huge bottleneck, which makes sense because nodes have to communicate with each other and then they have to transmit their data to each other. They also have to sync like model updates. So EFA will play a huge role in mitigating that bottleneck. So now we have a pattern or a way forward to scale up to hundreds or thousands of nodes with low latency internode communication. So some of the work that we did here was security harden the deep learning AMI that AWS has that comes with the EFA driver installed, and then we plug this AMI into Batch. The deep learning AMI isn't compatible with Batch out of the box, so we had to install the ECS agent, and we use Chefline Chef to do the installation. And Chefline Chef's kind of similar to Packer, if you're familiar with that. And then with an A100 GPU, you can attach up to 4 EFA network devices. So given that, users will be able to leverage EFA by running their training jobs with NCCL, and then we've also open sourced the integration with EFA in Metaflow so that anyone can use Metaflow, the Metaflow batch decorator, and specify the number of EFA devices that they want to attach. And then the next thing we've implemented is a high performance file system leveraging FSX for Lustre. And that provides low latency access to data with throughput levels of hundreds or even hundreds of gigabytes per second. So FSX for Lustre will be really useful when working with our terabytes of training data, so that instead of reading it in directly from S3 and saving it to memory or disk space, we can instead use FSX for Lustre to sync with S3, and then the user can pull in the data from the file system directly. It's also a parallel file system, so it handles simultaneous access from the multiple nodes of the HPC cluster. And then we integrated Metaflow with FSX for Lustre by using Metaflow's mounting host volume feature, so that in the batch decorator, you can specify host volumes and then target the mount path. So all of this work, HPC plus Metaflow array, the Metaflow array integration, is detailed in our internal tech blog. And yeah, I think that's pretty much it.